warm welcome to all of you. You have braved your way through the rains and Bangalore traffic, which must have been quite an ordeal. So I'm going to tell you a story of a neutrino today. So firstly, of course, I want to tell you what neutrino is, and then there will be some nice pictures and some big words. So we'll forget all the big words and we'll try to understand what it means, or in something simple terms or so on. But some of the words are left there and pictures for you to see that what it means and so on. So you know this thing which says Vigyan Samagam mega science. So do any of you know what is a mega science? Do you know what is science? Textbook. No. Is that all? So the science is about, when we look at it, is that what we understand everything around us, how things happen. And that's the cue, because and this has been there even before the school started, right? You want to understand how we came into existence, how the stars formed, how something happens around us, why tree grows. So all of this is a science. And you have now in the laboratories, you have labs in the school, you do experiments. So how is it like? It's like a small table on which you do some experiment. So these are the experiments when you do something simple. What has happened is over the years, it's not like that after studying science for so many years, we have understood everything. But when we want to learn something or find out some of the more deeper subjects or get a deeper understanding of a given subject, it is observed that now you cannot do an experiment alone. For example, let me take a step back a minute and ask you, all of you have handled a TV remote, smartphone, laptop, right? So now if each of these things, if I want to find out how it works, when the remote doesn't work, what do? Change the battery. So you open it, right? You open, change the battery. If the phone stops working, you have to open what it goes inside. So when something you want to find out how it works, before it stops working also, you can find out how it works, you have to open. Now if I have to open a phone, it's more expensive than opening a remote, right? So I'll need to look for that. So it becomes the same way. So if I want to study something for which it's going to cost me, I need to set up, look at something more, I need more money, then that requires more funds, more technical knowledge. Then when you want to build a bigger experiment, like you see somebody building a big dam, you do some work at home, 2 people come and do it. If somebody has to build a dam, you need thousands of engineers, hundreds of engineers to do that. So when you go to look for the experiments in science, where it requires a lot of effort, a lot of money, and a lot of technical knowledge, because it requires scientists, it requires engineers, and that necessarily really requires a lot of people to come together. And lot of people doesn't just mean one country, one city, or people in the city. Many of these projects which you will see in the exhibition later in the afternoon upstairs after this talk, there are 8 exhibitions. You will find there are hundreds of countries have come together. There are 4,000, 5,000 people involved in each of these. And that's when you say, because it's a collective effort of lot of people together, that's called a mega science. Now why we need it, we will see as we go along. I hope I can give you a flavor. So I'm going to tell you a story of something which is called a very tiny particle, which is there, called a neutrino. And just remember this word, I'll come back to it. I will speak for about 40 minutes, but it's not that I have to say something. Whenever you want something, you please stop me and ask questions. And I'm going to ask few quiz questions at the end of it. And there are, Nagaraj has promised me some exciting prizes for you people for the, at the end of the quiz questions. So many of you would have probably heard that in 1903, these 3 people, Henry Becquerel, Marie Curie, and Pierre Curie, got a Nobel Prize. This Nobel Prize they got was for the discovery of the radioactivity, which had happened few years earlier. How many of you have heard of it, radioactivity? Very good. So when Becquerel first saw it, he called it an X-ray. X because you don't know what it is, right? So that was discovered. Marie Curie is the only one who went on to win 2 Nobel Prizes. She got one more later in the chemistry. And she invented this term radioactivity. Soon after that came Mr. Rutherford, and he told us what it is the things are made of. Today if I look at it, as we said, we want to see inside a remote you look at. If I want to study a stone, I'll take it. So if what we are made of, if we look at, we break down the constituents, you'll find we are made of atoms. And inside the atom, there is a nucleus at the center. Now how that, and this concept that there is an atom in which inside the atom at a very center, like you get an apple, there is a core of the apple. you see a nucleus. That was given by Rutherford, and that's why he's called father of nuclear physics. Today, I mean, I may give you some examples of how things were discovered, but also what mostly we know today. So if now let us see, when we said nucleus is tiny, let us try to understand how tiny is tiny. I'm not going to give you the scale of length or anything. What is your height? 5 feet. So that's roughly 1.5 meter, right? So we are talking about a meter scale. Then when we take something else, if I take this, this will be few centimeters. So now you go smaller and smaller. When you look at a scale, you will see a millimeter. But when you go down, when you are talking about atoms, they are tiny. So how small are they? So they are much, much smaller than this millimeter and meter lengths which we talk about. So atoms usually are of the size of the angstrom, and this, if you have looked at the light and the wavelength of the light, that will come in that length, hundreds of thousands of angstroms will be light wavelength. But now when we talk of a nucleus, so that's where I have put it here, typically a size, the hydrogen is the simplest nucleus and an atom because it has only one proton. When we talk of atom, it has this tiny nucleus schematically shown here, which is sitting at the center. It contains positively charged protons. Then there are particles, neutrons, and the electrons float around inside. The electrons are negatively charged. So now when we have two charged particles, we know there is an attraction if they are oppositely charged. There is a repulsion if they are same charge. But inside the nucleus, you have positively charged protons sitting together. So there is something else other than electrostatic force works, and because it is strongly putting them together, it's called strong force. So what is the scale of the size? Let's look at it. If I consider the atom to be the size of the earth, then nucleus compared to that earth is as small as your Chinnaswamy cricket stadium here. Do you watch cricket? Typically they tell you that the boundary is at 70 meters boundary and this stadium is at 75 meters. So if you really look at it, the size of the earth, the radius is like a 6,500 kilometers, and the nucleus is the boundary will be around 65. That's the ratio. That's this tiny, tiny nucleus inside the atom. And why do I need to know about it if it is so tiny? Because even though it's very tiny, it's very, very heavy. All the mass of the atom is actually concentrated in that tiny atom because the electron is very light. So all the mass is in the proton and neutron. Typically, I mean, before we get into this number, you know what is the density of the water? Yes, so that's like a 1 gram per cc water. So if I take this water bottle, this is about a 500 ml, 500 ml bottle, this will weigh half a kg. But if you take a nuclear matter, or if you look at a nucleus, the density would be this enormous number. 10 power 11 means that means like billions you can. So just to give you a feeling, if I have a 10 gram gold coin and this gold coin was made of nuclear matter, it will weigh about 100 kilotons. And there are some stars in the universe which are called neutron stars. They are made of nuclear matter. They are much, much smaller compared to the sun, but they weigh much higher than the sun. That again is shown. So this is just to give you a flavor that if I peep inside the nucleus is so much different than what we are, though we are all made of nucleus. So when we get to that scale, there are different properties. We need to understand how these tiny objects interact, what makes them decide that hydrogen exists as a hydrogen, helium, what decides that sometime hydrogen will become an helium, two hydrogens will come together and make a helium. What will decide something which is heavy like a lead or uranium will come down into hydrogen or come down in the lower downs and come down. It doesn't come directly into hydrogen, but can I bake it into that? These are the things which you want to understand, and when we do it. So just to summarize what I said so far, if I peep inside the atom, I have a nucleus concentrated sitting there and which is made of neutrons and protons, and I have electrons outside. So now next question comes in is, since the nucleus is strongly system there, why don't I have all possible combinations of neutrons and protons? I have a hydrogen which is the simplest of a nucleus which has one proton. But I also make something called a heavy hydrogen, deuteron, which has one proton and one neutron. I have a helium which is the next element. You must have looked at the periodic table, right? But you can go to oxygen, you have fewer elements. But as you go to the heavier elements, like there are elements like tin, you find that there are many isotopes of tin. Means it has the same number of protons, so it has a similar properties like tin, but it has different neutrons. So you get different isotopes of them. But before I get into that when we say some are stable, some are not stable, that means I can, if I was like cooking, I may mix some neutrons, protons, I can make some nuclei which will live long and some don't. And this is not just something what we will do today in the lab. This is what happened when the universe began, or as we believe that it began with a big bang, how the elements got formed and how the different elements have come into existence. Some got formed, some things were stable, some things were not stable. So what was one of the puzzles that came along with that? It was found that neutron is slightly heavier than proton, and a neutron left to itself would like to decay. So neutron goes into proton and electron. Neutron has no electrical charge, so when it decays, you get one positive charge, one negative charge. Very good, charge is conserved, no problem. Now we know that we also have to make sure that we conserve the energy and momentum. These are the basic things which we conserve in the physics, because otherwise the universe would not be as it is. I can create energy, I can create momentum and so on. So when people were looking at that, it was expected that if you do like a chemical reaction, there will be a Q value of a reaction, which is also called binding energy in this thing. So I should have had an electron with a specific energy. If I take a neutron at a rest here and I let it decay. But that did not happen. What was found was the electrons, if I did this experiment with 100 neutrons, the 100 electrons came out with a different energy. And that was a puzzle. So when you say something like this happened, this was way back in 30s when very little was known about the different particles and so on. So then it was postulated, and that is the birth of neutrino, was that we have to conserve energy and momentum. So Pauli said that such a thing is possible, that if neutron goes not only but into proton plus electron, but also third particle, which I cannot see. Why I cannot see it? Because it doesn't have a charge. If it had a charge, I would have been able to see it. So it doesn't have a charge, and it's very, and then it takes away the energy. So because it was called a small neutral particle, it was called neutrino, because INO in Italian refers to a small thing. Later, of course, Fermi, another great scientist, came and explained how this process could happen. And in this, for all these fundamental particles, there is a concept of a spin. You could think of it as an analogous of the spin of the earth, which is there. So you know there are particles which are considered as a spin 1 particles, and there are particles which are considered as a spin half particles. So whether you are 1 or a half integer or a half integer, they fall in a different group. If they are half integer, they fall in the Fermi group. If they are 1 integer or the integral integers, they fall in a Bose-Einstein group. So I will not go into further details in that, but if somebody is interested, we can talk about it later. And then, because this particle is there but you don't see it, we said, okay, it is mostly there and it just goes through and it remains ambient. I don't see, I'm not able to see it. So it is a very weakly interacting particle. Let us, and this is just an example of that. So what happens, I mean, just to again summarize the story of neutrino, in a nucleus which had Z protons, when a neutron converts into a proton, you get an extra proton. So if I started with now you see when the beta decay happens inside a nucleus, you actually change an element. So you are this is how the nature created elements. For example, let's take oxygen. So if the oxygen has 8 protons and 8 neutrons. Now if the one of the neutrons underwent beta decay, it created 9 protons. As a result, you had 9 protons. Now what is element Z equal to 9? That is fluorine in the periodic table. So in this process, not only something changed in the nucleus, but now your property of the element changed. And that is how the different elements got created, is one of the ways of getting different elements created. So that got created, and this is how the spectrum will look like. Let's see. Another important thing that was found with neutrino was the nature, as we said, energy and the momentum. We also like to see that many of the cases, you know this, I have this what is called the left-right symmetry. I have 2 hands. If I take a mirror of the mirror reflection of this turns into, right? Does it turn? Yeah, so but it is not identical, which is there. But if I have a round object or a cylinder object, if I look at a mirror reflection of this object, this would be symmetric, reflection symmetric. So it was also observed that whenever these neutrinos, or the looking at the interactions of the neutrinos, they are not quite follow this mirror reflection symmetry. Their mirror image is different than the object. Now this has lot of technical implications, and this is technically called parity study, and Madame Wu was one of the woman scientist experimentalist, very noted experimentalist. She carried out this experiment to show that weak interaction involving neutrinos actually does not follow the mirror symmetry. This was quite a landmark experiment, very involved, but just to remember that's where I mention it, though it's a little technical here. Now, so where are the neutrinos generated, and how were people trying to look for? So in 30s, I told you, if you remember, in the beta decay 1930s, the existence of neutrino was postulated. But did we find the neutrino? We said it should exist. Somebody told us that it is there. We say if it is there, something like this will happen. But experimentally, I should be able to measure. Finally, that is what we've said. I am an experimentalist. So I'll tell, all right, all great theories and all that, proof of the pudding lies in eating. I want to see a neutrino. But it's very difficult to detect, and it took almost 25 years later, 1956 it was found, and I'll tell you where it was found. So where do those neutrinos come from? One of the major sources of the neutrinos is the sun. Because where we get the light from the sun, it happens because of the fusion inside the sun. And where you have the hydrogens combining, they go through a series of reactions, and finally you get very many neutrinos coming in. The reason I mention this, because this was one big puzzle. And this also told us something more about the neutrinos. So the beta decay told us that neutrinos should exist. It is a very light particle. It could be a zero mass or something. Other experiments told us that somehow it does not like the mirror reflection symmetry. And then we said, okay, from the sun, so this should go on. Astrophysicists looked at it, they looked at a fusion, and they told you, okay, this is what is going on in the sun, and I should get X number of neutrinos. By then, if you move little 2 decades ahead and look at it, and further, I think today we know that there are many fundamental particles. By then you realize that protons and neutrons, which are sitting in the nucleus, are also not fundamental particles. I can further, I can open this and break into these further constituents. Proton can also be further broken into the constituents, and you can look at it's made of what is called quarks. So proton is made of U and D quarks. So there are families of the particles, and I don't give you a complete zoo, and Indu is here, she may later tell you about it if you want to ask her questions. There are many particles. So there are 3 families of quarks, which are called UD, CS, TB, and so on. And similarly, there are 3 families of leptons. So you have electrons, and each electron has its own partner, the neutrino, electron neutrino. Then you have cousins of these people, like muon neutrino, and similarly tau. So these are like heavier electrons. We will not go in detail on that. But then all these families, the way they interact, there are forces. Like you have a gravitational force. You have Coulomb force when you talk about the charged particles. So there are called charge carriers, which are bosons. These particles are named bosons on the after one of our great Indian scientists, S.N. Bose. How many of you have heard of him? Oh, very good. I'm very glad to hear that almost everybody has heard of S.N. Bose. We celebrate his 125th. Another thing which we have to look for understand about the particles is they all come in pairs. Each particle has its partner, what we call as an antiparticle. So the particles and antiparticles have same mass and opposite charge. This is because, consider going back to the universe. The universe started with a big bang. There was nothing. So now you created protons. So if you have to create protons, you have to create a lot of positive charge. So we cannot violate the charge. So if I create 10 protons, I must create 10 antiprotons. So the net charge is conserved. Similarly, if I create 10 electrons, I have to create 10 anti-electrons, which are called positrons, positive electrons. So essentially, we are made of matter, but then there was also enough antimatter was created. So where did it all go? So there should have been one speaker and one anti-speaker, and there should have been just light if they made together. So where did all that go? So that's a very open question today, and I will leave that at the end also for that. In case of photons, they are their own partners. They are because there is a neutral charge and so on. So now comes the question, which is the other neutral particle I know so far? I told you neutrino also has no charge. Neutrino is there. So does neutrino have another partner, or neutrino is its own partner? So that's also a question I want to know about neutrino. So all these things are there. So what are the questions we ask? Okay, how many neutrinos are there? I told you I have 3 electron families, so I know at least 3 should be there corresponding of the electrons. Is the mass of a neutrino 0 like photon, or does it have a finite mass? It's less, it's very small, agreed, but is it there? And is it its own antiparticle? So these are even today some of the open questions. So let me take you through some of the things which I have already said, maybe a repetition, but let's look at it. So where do the neutrinos come from? So you have neutrinos right from the Big Bang, when the universe began. Because at that time also neutrinos got created. And those neutrinos, because they are not interacting with matter very easily, they are still surviving. So these are the messengers from the farthest part of the universe and the oldest part of the universe. So if you look at these neutrinos coming from the Big Bang, you know what happened there. They bear that timestamp. So this is today your only signature to find out what happened in Big Bang. Big merit. You get neutrinos from the sun, as I told you. The supernovas, stars exploding, there also the neutrinos come from. So again you get information. There are atmospheric neutrinos because there are cosmic rays. As we sit here, there are a lot of charged particles coming from outside, and decays the neutrinos come from that. And the big effort which we are talking about, this INO, which will look for the large detector, this actually will be mainly concentrating on studies of the atmospheric neutrinos. And I must say that a major work on this, the discovery of the atmospheric neutrino, was done in 60s, not very far from here in the Kolar Goldfield mine. There was an experiment which was set up there. Then, of course, there are neutrinos also coming from the core of the Earth. What is there at the core of the Earth? Lava, yes. So there are more radioactive elements in that lava, molten, and they are beta. So if there is a beta decay happening, there will be neutrinos. So then also you get the geoneutrinos. So it also tells you what all is inside there. And then there are man-made sources like accelerators and the reactors. So are you bumping into a neutrino? Do you think you are bumping into a neutrino? Yes. Okay, good. So now you can look at some of these numbers to see how many neutrinos you get there. So you get there absurdly large numbers. Neutrinos will be coming in from the 400,000 billion neutrinos coming in from the sun, 50 billion neutrinos coming from natural radioactivity. So large number. But do we need to worry about it? No, because the neutrinos will just zip through all of us, and you can count these zeros later what is coming in. What is more interesting, and I want to stress this because these days everybody feels radioactivity. Each of us, our body, contains about 20 milligrams of 40 potassium. 40 potassium is an isotope of 39 potassium, which is radioactive. So we have potassium in our body, a certain fraction of this is 20 milligrams will be the radioactive fraction. So which means each one of us emits about 340 million neutrinos per day, and they are traveling at a speed of light. So don't ever feel depressed or bad about anything. You all are very scintillating personalities, right? You are emitting so many neutrinos. So I promised you that we started discovered the neutrino in the 1930s, or postulated in that. The experimental discovery came in 1956. Because it was very difficult, the Nobel Prize came even much later. Only actually one of them got the Nobel Prize. And because the prime condition for Nobel Prize is you have to, of course, do a very good physics work, but you also have to be alive. So this discovery was made in this experiment. Now, when I talk about experiment without going into the details, I just want to tell you that people talk of detectors. What is a detector? When you see something, your eye is a detector, right? And then you tell and you look at it. So here also, the experiment was very simple. You looked at an antineutrinos. The concept of the experiment was simple. Antineutrinos from the reactor. It reacts with it is captured by the proton, and then you make a positive electron. But the positive electron, unlike a negative electron, is not a very stable one. So as soon as a positive electron meets a negative electron, its partner, it comes out, they mix together, or what is called technically annihilate, and emit 2 light photons. And those light photons you detect, and then you can find out with various correlated things. But you look at the size of the experiment. It said a 400-liter tank. How big you think a 400-liter tank would be? Have you, yes? How big would be roughly? Have you seen, have you seen a water tank in your building? So what is the typical capacity of that water tank? 100-liter water tank won't last one family, it will not there. Okay, so go back and think about it. Find out what is the water storage capacity of that. 1,000-liter also will not last for the building. Okay. What is the volume of your flush tank in the toilet? 10,000 liter. Okay, we are getting into this one, but all right, flush there. So this is not a very big size. 400 liter is still a small size detector. That is what I was trying to tell you. Then came a more interesting experiment, because at that time we knew that okay, sun also should send us the neutrinos, and sun should be making the energy which is there, burning hydrogen at a rate which we people calculated, and so on, and so what should come in. So then Raymond Davis did a very clever experiment in Homestead gold mine, and to the best of my knowledge this was the first underground experiment where he went deep down into the 1.5 kilometer in mine, because it's like if you want to listen to me and if there was lot of noise, we'll have to shut down the windows so that the outside noise is reduced. So when you want to look for neutrinos, which are weakly interacting particles which are there, which I want to detect them, I have to shut out all the noise and improve my ear sensitivity so that I can look at small things. So he went underground to cut out lot of background. And what did he do and what they found? So now I don't want you to look at too many details in it, but what I want to show is people expected to see something like this tall bar, that you will expect so many neutrinos, and what they measured was a very small number. So obviously what happens? If somebody comes and tells me if I have an experiment, I said I found small number. I was told go and repeat the experiment, you did a mistake. So go repeat the experiment, same answer. Somebody else does the experiment, same answer. People went back and did the calculation, same answer. So what is wrong? What could be happening? So then they concluded that the neutrinos must be doing something strange. Now to explain this to you that what neutrinos do strange, I'm going to use a very qualitative example. I hope Indu will pardon me for this, because this is a concept of oscillation. See, you are from one school, right? Here. So let us say, you are from which school? Okay. So I will call you school A. Let us say we have another school which is coming in there, school B, and both the people have come. And you are all recognized by your uniform, which is coming in. And I know that when you entered the thing, the entry guard said that school A, 50 kids have come in. 50 neutrinos should have come in here. So in this room, I need to count 50 students. Your teacher gets up and says, counts and finds that there are less. You do double count, same thing. Then again you find out, but the people entered here, they all should have been here. Then they say, okay, maybe the students are naughty. They have brought different uniform jackets and they have changed uniform jackets. So count total number of students. It works. So the neutrinos do something like this. They start as, so in the sun, there was a hydrogen-hydrogen fusion generating electron type neutrinos. So neutrinos belonging to one school. And they all should have just come to the earth as it is there. And because I'm sitting here and counting electron type neutrinos. But the neutrinos did something small, something smart, something naughty on the way. They changed their uniform, they changed their form, they went to a type B. So if I just counted type A here, electron neutrinos, I found them less. And but then where people went ahead and did an experiment, which is there, I'll come back to this experiment details later. You find, and if you count total neutrinos, then you find, okay, then they are as expected. Now what does this happen? So this is a thing called neutrinos oscillate. They go from one type to other type. And why do they decide to do that? How do they decide? Consider like you were coming just from the security to here. There's a very small distance is there. But if I let you people all move through the whole building, or you were running some marathon, the longer the race you ran, there's a larger chance, larger probability for you to do this change or do the mischiefs, do the oscillations. So whether the neutrinos oscillate or change from electron neutrino to the muon neutrino depends on its energy, depends on the length it travels and so on. But this is a very unique property of the neutrinos, that they change from one to the other part. And what does it tell us? Why it is important that they do? It now tells you that neutrino has a finite mass. It's not a zero mass. It may be very small, but it has a finite mass. It's not at all a zero mass. So we learnt one thing about neutrino. It's like electron spin half. It also it doesn't obey the mirror symmetry, and it has a finite mass. So how was this experiment done? Just to give you an idea that what it requires. This experiment was done at 2 places in a big laboratory in Japan, and we started within the first experiment was about 400-liter tank. So now I want to give you the scale. This experiment, which was done in Canada and Japan, this had 1,000 tons of heavy water. This is the deuterium water, that is the heavy hydrogen water, and it has this size. I think there is a human being standing here, so you can see the size of the experiment. And these are the mega science experiment. These kind of experiments you cannot build alone, you cannot do it alone, and you need a lot more expertise and a lot more things, because you need engineers to build this, you need engineers to help you design the different detectors, you need electronics to make these signals, process it, physicists, theoreticians, everybody is required for that. In fact, this is a nice picture which is also available on the web, which you can see when they want to repair a detector, there are people going around on the boat inside the water tank to repair that. That is the scale of the experiment. In fact, you will see this probably happening in Bombay, Pune right now, because there are so much floods there which is coming in. And these people, MacDonald and Kajita, got a Nobel Prize in 2015. In fact, if you see the exhibition upstairs, you will see more details on all the Nobel Prizes in the neutrino related work and so on. So they said the neutrinos oscillate. So now comes a question that is the neutrino, it doesn't have a mirror symmetry. So there are left-handed neutrinos, there are right-handed neutrinos, and so on. But main question let us ask now, like a photon, is neutrino its own partner or not? And that is the question which we want to ask. That's the which we want to learn. We learnt about neutrino from a beta decay. So now when we want to learn about nature of neutrino, we still go one step further than the beta decay, and that's called the double beta decay. And Maria Goeppert-Mayer, another woman Nobel laureate, she talked about gave the concept of double beta decay. So what happens in the double beta decay in nuclei? I told you in the very beginning, if you remember, that not all proton-neutron combinations are stable. So why does that happen? It's like this staircase. If I put a small ping pong ball here, it may stay, but with a little push, it will go down, 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 and it will like to go and sit at the bottom. So when you have nuclei with a neutron-proton combinations, they are like that. That depending on their binding energies or Q values, with a little push, it will like to come and like to sit somewhere at the bottom, where it is most stable. Then it is coming in. So then what happens is that, so if it is sitting on this upper stair, that means it can convert, one of the neutrons can undergo beta decay, and it can go down to the lower state. It will go. But then if the staircase is jagged, sometimes it cannot go by one proton emission. But if two neutrons decide that they will together decay and go, it can happen. Now this becomes a very rare process, because consider in a class of 30, 40, if people have to work in synchronous. It can happen, of course, when you are singing in orchestra or something, but two people doing something randomly have to simultaneously agree to do something. Doesn't happen. Neutrons also do the same thing. So it's a rare process. So that can happen, and in such a case, then you have the two neutrons decaying together, you have a double beta decay. Now what are the time scales, what are the probability that it happens? Beta decay is a weak process, that's why the sun is living for 10 power 10 years. If it was happening very fast, all hydrogen would have burnt and it would have gone away, coming in there. Double beta decay is a doubly weak process. So it will be 10 times 10 multiplied by 10 times 10 slower. And then you look for a special process in double beta decay, which is the neutrino-less double beta decay, because where I said I had a neutron which is going into proton, electron and neutrino, antineutrino. Now if antineutrino is its own antiparticle, these two antineutrinos, like electron, positron, annihilate, and only two electrons come out. That is the neutrino-less double beta decay. So if I see this process happening, that I look for the two neutrons decaying into two protons, and I see no neutrino coming out, then I can tell you, aha, neutrino is its own antiparticle. And how can I experimentally look at it? I look at it experimentally by measuring the energy of the electrons. I look at the sum energy of two electrons. What you expected in beta decay when there is no electron? Electron should come out with a given energy. Here also 2 electrons should come out with a given energy. So I want to measure that electron energy precisely. And so these are the experiments which are done. So forget the write up on that. I want you to look at a picture again. So this is a one very large experiment working at Gran Sasso in Italy. Yeah, I'll finish in under 5 minutes. Yeah, at Gran Sasso in Italy. So this is again a human being, and you have this huge vessel of copper, very pure copper vessel. And then you put germanium diodes inside it. Some of you have heard of diodes? Yes, so you put germanium diodes inside it because germanium itself will double beta decay. This whole thing is put inside something called liquid argon. Have any of you heard of liquid nitrogen? Yes, so liquid nitrogen, like that you make a liquid argon because you can cool the detector, it works. That main thing is all these things are done, complicated detectors, so that you can identify what is happening inside. Because when you say you are looking for a very weak signal, which is happening here, something could be coming from there, like here, the light is coming from here, light is coming from there. So if I want to look at, I need to shield all these light coming from all the sides and look only at the center. And that is what is done, and that's what makes the things complicated. This is another experiment. So this is also like you can see a string of detectors, which is again sitting here. And again multiple layers of copper vessels and lead and so on. So look at the scale, the size of a detector, 750 kg detector. And you take all of that and cool it down because you want to make it very cold. It's a calorimeter detector, I'll tell you in a minute. So you want to cool it down to what? I cool water down into the fridge. I make it ice that goes down to 0 degrees Celsius. But you can take it even further down. But since you know liquid nitrogen, it will go to what is called 77 Kelvin because room temperature is 300 Kelvin. So you go to liquid helium temperature, you will go down even further. But here you go down to millikelvin temperature. That means to the order of actually 10 millikelvin will be like an 1/100th of a Kelvin. So why do you go so low? I'll tell you in a minute. So we are planning to do an experiment with a tin detector, and a detector will be a calorimetric detector, which is I will show you here. So what is the idea? The idea is you will have a tin sitting here. It will undergo a double beta decay. There will be electron energy, and because you are keeping this at a so very cool temperature, as soon as the electrons come out, there is an energy. What will happen? Consider a school experiment. I have a copper calorimeter, which is kept in ice cold temperature. And I drop a hot solder iron drop, or I drop some hot water. What will happen? Temperature will increase, right? I had cold water, I mix some hot water, temperature will go up. And if I can measure that temperature, how much it increased, how much temperature it increased, I can tell you how hot was the water if I say I added 5 ml water. That's exactly what you do. You keep it cold because then measuring a change in the temperature is easy. If it was boiling water 100 degree and I want to make it 99 degree and I make it 100 degree, it's difficult to measure. If it is 0 degree, 0 to 1 degree, I can measure easily. So you make it cold and then you measure the temperature change. So I also need a good thermometer to measure that, and that's what the whole experiment is about. That you go to so we have making an experiment which will work at achieves about 10 millikelvin, so that is 1/100th of a Kelvin, and you do the thing. So I'll skip this and I'll come to something else which I wanted to show you here. So here I already also mentioned the lead, when you surround something with a lead. You know, people use, this is a kind of effect you will see. Many of you would have seen the noise spectra when you run the amplifiers for the sound. You know, you get the things coming in. So this is when you say you go underground or you shield the things, you surround it, you start seeing improvement. You cut down all unwanted things and then start looking at things which are of interest to you. This is just to illustrate that. And people use here for things like Roman lead. The people have recovered the lead from the ships which were sunk in Roman time. That is how many years back? Roman era. 1,000? 2,000? 100,000. What is the age of the universe? Maybe almost that. No, keep this. I will come back to this as a quiz question on the end. Yeah. Next time I will give us to talk on the asterisks. So it's 2000 BC, no? So neutrino, so what we need to know now, looking all this, and I hope some of you will grow up to provide answers to these questions, is neutrino mass. How much is, what is the mass of the neutrino? So if you look at the neutrinoless double beta decay, if you can measure that, you will be able to tell me whether it's its own antiparticle as well as what is the mass of a neutrino. Is its neutrino its own antiparticle, or neutrino and nu are different particles? And then the question which I asked you, why there is more matter than antimatter in the universe? It's not directly related, but it will be related. But I am sure some of you will have to provide answers on this. And these are the students and people who have, some of the students working on this, going there. And I thank the INO collaboration. You will please do visit the exhibition outside on this. Okay. So before I go to quiz questions, if you have any questions, thank you.
So it was also written that it takes 10 to the power 10 years for neutrinos to, for decaying, beta decay. So how does it happen?
So the beta decay is I said 10 power 10 years is the age of the sun typically. Now this is a weak interaction, so different nuclei have different rates of beta decay. The free neutron decays, the half-life what we call decay rate is like a 10 minutes, but then there are nuclei where the decay rates are much slower. But it is the time scale of this process compared to the other nuclear reactions is much weaker. This is a very good question. Okay, who got the Nobel Prize for the discovery of radioactivity? Yes, yes.
Marie Curie.
That's question is there. Who got the Nobel Prize for the discovery of radioactivity?
Marie Curie.
It's correct but not complete.
Pierre Curie.
Yes. Still not complete.
How many? One more, right?
I can't answer. Yes.
Henry something, Henry B.
Okay, good. You get it. Yes, Henry Becquerel. 3 people got it. Yes, very good. Okay, second question. When did Rutherford get the Nobel Prize and in which subject? Wait. Don't answer. Yeah, here. 2000? 2002. No. Wait. Yeah. Yes. Which subject was right, but that is only a partial answer. 1988. 1908. Okay, I didn't hear that. Okay, fine, but you didn't say chemistry. The first was, okay, anyway, you get the prize. Fine, all right. It's okay. I couldn't hear 1908. I heard something else. Okay, sorry. 1 minute, I lost the track. Sorry. Yeah. Okay, now this is the third question. So in this talk, how many women scientists' work was mentioned and how many women Nobel laureates were mentioned? There are 2 parts to the question. Yes? No? 2 Nobel laureates and 4 works. 3 works and 2 Nobel laureates, yes? Which is the first? No, that's okay. No, 3 and 2 is correct, come on. Okay, now neutrinos can pass through Earth, true or false? Okay, so good. This is very good and this everybody deserves an answer. Or maybe I deserve a prize for it. Okay, now this is my real last question. I want you to ask this one. The number of neutrinos in this room has increased during the course of this talk. True or false? True? Everybody agrees or don't agree? So at this rate, the neutrinos will keep on increasing only? False? You have to make up your mind. It's true or false. You are saying both. Yes. Good. Very good. Thank you.
Yeah, what's your name?
Priyanshu.
Okay, Riyanshu gets prize for answering a question, and someone else. Yeah, what's your name?
Pushkar.
Pushkar gets another prize for answering a question. Okay. Who? Okay. Yeah, there's one more. So, what's your name?
Aditya.
Aditya. Okay, congratulations. So,